The next intervention will focus on two aspects of data challenges. Emeric Florac works at the Health Data Hub as a data scientist, and he will present us the basis of machine learning applied to health. And then Maximilian Oppelt, who is a research scientist at the Fraunhofer Institute for Integrated Circuits in Germany, will share his testimony as a challenger and present the interest of participating in such data science competitions for challengers just like him. You can start.
Thank you, Agathe. So I'll make a short introduction in machine learning since it's what we are going to be talking about this afternoon. First, from a theoretical point of view, really short, a brief history also, and finally, a concrete application in health data science. So, generally speaking, what is machine learning? It's when you have data, which is made out of features and targets. For instance, you can have pictures of cats and dogs. This will be features, and targets will be cat or dog, the label of corresponding to your features. So you have these data sets, and you have targets that you want to predict. You have a model and a training algorithm. The model, you will be trained through the training algorithm. And what you are going to do is to bind it all together to make a trained model. And a trained model will take new features in as an input and will output predicted targets. So with our first example, you will give it a picture of either a cat or a dog, and it will output a cat or dog. So if we look a bit backwards in the past, it's quite a recent field, actually, machine learning. It started in the 1950s with very simple algorithms. At the early beginnings, it was mainly symbolic logic that was applied, so hard-coded rules. Then in the 1960s, it shifted towards Bayesian methods. Bayesian is more probabilistic-based methods. Then in the 1970s, there was a so-called AI winter, AI for artificial intelligence, and winter since there were no major breakthroughs during this whole decade due to a lack of funding and a lack of computational power, because machine learning is very, very demanding in terms of computational power. In the 1980s, there was a rise, so in computational power, but also in the interest that machine learning sparked in the industry. In the 1990s, it was the end kind of symbolic logic. So it shifted entirely to data-driven approaches. So you forget about hard-coded rules and you just take care of data itself. So it's really more about statistics then. At the beginning of the 21st century, you have kind of an explosion in the use of machine learning with a wide variety of models that had been developed but not really used, not really adopted by the industry, such as support vector machines, ensembling methods, boosting methods, and so on and so on. And quite recently, at the beginning of the 2010s, you have the beginning of the deep learning epitome. Deep learning is really machine learning with neural networks. Neural networks, you may have heard about them, they're quite everywhere now. And since then, it's been quite a supremacy of deep learning. Just a little bit more of theory, you have essentially three types of machine learning. The first type, which is the most common, will be supervised learning. Supervised, so you have your data, features, and targets, and you know what your features are and what your targets are. So it's the example with cats and dogs pictures. Unsupervised learning, in your data, you have only features, you have no targets. The point is to try and gather your data points in a way that makes sense from a statistical point of view. So that's the so-called clustering algorithms. And finally, you have reinforcement learning. In reinforcement learning, you have an agent, which will be the learning agent, that you plunge into an environment and it interacts with this environment and learn from the interaction. An instance can be the chess playing neural networks or Go playing neural networks, which have made quite a fuss recently. Some popular applications of this kind of methods. So you have natural language processing. It's understanding speech, basically, language more precisely. Computer vision. So it's very widely used here for data challenges in medicine. You have pictures and you want to predict, for instance, whether there's a tumor on it or not. Speech recognition, recommendation system, quite popular for YouTube, for instance, for Netflix and all these kind of websites. Generative models, which is creating data out of the blue, and trends prediction. So now I'll just dive into a project I've been working with at the Health Data Hub. We've been working with a startup which is called Implicity on the problem of predicting heart failure crisis. So heart failure is a chronic disease with acute phases, and most acute phases could be prevented if they were predicted. So the point of the project is to have pacemakers, which play the role of a remote monitor for a patient. And with the data of the pacemaker, you try to predict acute phases of heart failure. So in terms of data, what we have is data which comes from the connected medical device, so the pacemaker. It's data which comes on a daily basis. So you have, for instance, heart rate, activity percentage, and so on. And you have also claims from the National Health Insurance. In claims, you have drug prescriptions, you have doctor appointments, and you have, of course, heart failure crisis. How can we link this to the first slide I presented you? You have a phase that's called feature engineering. So you take the raw data and you extract features from it. So you have a first phase, which consists in extracting features from the pacemaker data. And you have another phase, which consists in extracting features from the claims data. And most importantly, extracting targets from the claims data. And targets here will be the dates of the heart failure crisis. Then, with a carefully chosen model and carefully chosen training algorithm, you bind it all together, and hopefully, in the end, you have a model that is able to predict whether a patient will have a heart failure crisis in a few days based on its pacemaker data. Thank you for your attention. I hope you learned something today.
Thank you very much, Emre. We will now move on to Maximilian's presentation. Attends. I think he's connected online. Maximilian is in Germany right now, so.
Yes, hello, can you hear me?
Yes.
Great.
Hello, Maximilian.
And you can also see my screen?
Yes, as well.
Great. So thanks, first of all, for inviting me. I want to give you a small insight about why we compete in these challenges as research scientists, data scientists, or data engineers. So the complete field, why we are interested in it. And my name is Max Oppelt. I'm working with the Fraunhofer Institute for Integrated Circuits and the Machine Learning Data Analytics Lab of the Friedrich Alexander University, Erlangen-Nürnberg. And part of my work is financed by the Ada Lovelace Center. So why did I compete in a challenge in the past? And it was part of my scientific journey or my CV, and therefore a small background to myself. I started doing my Bachelor of Engineering, Mechatronics, then my Master of Science, and then I went straight to the industry. I did a lot of product work. I was image processing software engineer, image quality engineer. And after a while, my interest in doing the academic research again rose up in me again, and I started working at the Fraunhofer Institute for Integrated Circuits. I'm sorry. And at the very beginning, as a research scientist, as a junior research scientist back then, you need to look for a topic that really matches your interests. And one way to do it is looking for an interesting challenge out there. And I selected the FusionNet challenge on the Computers in Cardiology Conference 2020, where we tried to detect arrhythmias and 12-lead ECG recordings. And participating in this challenges was very, very beneficial for me, because it was closely related to the topics our institute is working on: biomedical signal analysis, software engineering, embedded design of new sensor technologies, clinical studies, and a lot of machine learning, deep learning work, all financed by public sector. And this at the end landed me a new position as PhD candidate in the machine learning data analytics lab, Friedrich Alexander University in Erlangen. So a small key messages why I participate in this challenge, and why a lot of students of mine participate in these challenges, is that people want to employ their theoretical novel methods to a real world problem. So they're constantly looking for new data aside from typical toy data sets used in publications. It's also very interesting to compete with others. So you have instant feedback, how good you're performing, how your method is performing. You have a leaderboard, and you're extra motivated to bring in additional 100% to solve the issue. It's also nice for a young researcher, or even for a senior researcher, to network and meet new collaborators, that you can build a new network in the academic area or in the industrial area. Coming back to the Computers in Cardiology Challenge 2020, it's also nice that you can travel to a conference, which was in Rimini, with a very nice weather, and write a publication about your work. Then I was asked why, or what key ingredients do you need to build a successful challenge if you want to host your own challenge. Certainly, it's about winning a prize, winning money, exploring new domains and techniques. But I think 4 important ingredients are: first, you need to integrate the participants in your problem, in your framework. For example, let them discuss about the problem, about the rules, let them frame their own metrics and their own background, and bring them into the challenge to keep them going while the challenge is running. It's also important to build a community, start a Google Groups, Discord, or a live event that competitors can meet and talk about the challenge to build a community. Also, interesting side note is that you should choose your metrics wisely. There are people out there that try to exploit your metric and find local optima that may be not beneficial to the area, because machine learning is very sensitive in this direction. And a small side note, because a lot of my students are competing in such challenges nowadays, is that you should keep the pedagogical thing in mind. So you're teaching young researchers to explore a new domain, and do not exclude those. Especially with young researchers, you're able to build a community that will last for a longer time. Some tips for participants: read the rules and report flaws. Don't use them. It's not fair for other challengers, and it will not bring the community as a whole to a new level. Make sure the challenge is a good fit for you, the topic is a good fit for you. Communicate and network with other teams, and continuously submit your work. Start simple, and then increase the complexity and the ability of your model during the challenge. Try to gather domain knowledge. Do not simply employ novel methods to the problem, but also think about the domain. If you're thinking about ECG, why is it generated, or other domains, think about the domain. Track your experiments, and the most important thing is probably you should have a lot of fun doing the challenge and keep going. What will I do in the future? I will certainly try to participate in one of the challenges you will introduce today, and I'm looking forward to hear your presentation. Thanks, have fun.
Thank you very much, Emric and Maximilian, for these presentations and elements. It's really interesting to see how and why challengers decide to compete in data challenges. We have one question from someone online. It's for you, Emric. Yes. So, can you elaborate on the specificities of AI in health data, privacy, usage control, cost of errors?
Okay, so I try to make it short because we could speak for hours about this kind of subject. Privacy is not in fact related directly to machine learning. It's more about what comes before and how you can use the data. Do you have the rights to use the data? Is it protected enough, and so on and so on. Concerning cost of error. This is a very interesting topic actually in healthcare, because, well, imagine a situation where you have I don't know, pictures of skin or something like that, and you want to detect a tumor on it. Chances are your dataset will be very unbalanced, since tumors are hopefully not that frequent. You'll have very few images with tumors. So if you base yourself only on am I right when I say there's a tumor or not, chances are you'll have a very good score, but still you will fail most of the time if you say there's never a tumor in it. You'll be right most of the time, but it's not good from a medical point of view. So it's all about the choice of the metric and how you evaluate your model. This is really, really topic dependent and must be discussed with physicians or doctors and so on.